In the previous lecture, I discussed how someone falling into a black hole would be ripped apart by tidal forces and finally crushed into a tiny volume at the singularity. But the equations of Albert Einstein's general theory of relativity suggest that, in fact, black holes are connected to passages through space-time known as wormholes, so named by John Wheeler in 1957. At least in principle, it might be possible to use these wormholes as shortcuts to a different, distant location in our universe, or as gateways to other universes perhaps, or maybe even to travel backward in time. Now, would that be great or what? This concept has been used an awful lot in science fiction books and movies, including Star Trek and Carl Sagan's Contact, as well as in TV series such as Farscape and, Sliders, Stargate, Strange Days at Blake Halsey High, series like that. It's a wonderful concept that a lot of TV shows and movies like to capitalize on. Well, in this lecture, we'll explore black holes in more detail to understand what really happens. Do shortcuts to distant parts of our universe or even to other universes actually exist? Is travel back in time to the past really possible? Be amazing if it were so, but let's explore this to see if it really is true. Note that mathematically, there are several different kinds of wormholes, but here I'll discuss only those wormholes whose entrances are connected to real black holes having event horizons. I really won't have time to include more than a brief mention of idealized wormholes, vacuum solutions to Einstein's equations, devoid of energy, and not having horizons. Well, let's start our discussion with non-rotating black holes. These are known as Schwarzschild black holes after Karl Schwarzschild. Mathematically, space-time can be thought of as flowing inward toward the black hole. It goes faster and faster as you approach the event horizon. The flow speed reaches the speed of light at the event horizon and is even faster than the speed of light inside. Therefore, nothing can get out, not even light. If it's trying to get out, but it's not going at the speed of light, or even if it is going at the speed of light, but space-time is flowing in faster, then the stuff can't get out. That's the idea. So one can think of a black hole as being like a cosmic waterfall or a bathtub drain in space. Fish can swim upstream near a waterfall as long as they are faster than the downward water flow. But since the water goes faster farther down the waterfall, at some point the water flow is faster than the fish can swim, so they just go down the waterfall. Here's a diagram illustrating with these arrows the flow of space-time into a black hole. It's relatively slow far outside the event horizon and gets faster and faster as you go farther in, reaching very high speeds exceeding the speed of light after the horizon. And this excess of the speed of light is not in violation to anything in relativity. Space-time can indeed flow faster than the speed of light. To further explore the structure of black holes, I need to carefully define what I mean by curved space. We've already seen some diagrams illustrating it, like the elastic sheet with the heavy ball. Let me show it to you again right here. Here's flat space, but if I put a heavy ball into it, Earth's gravity brings it down, simulating the conditions of curved space, indeed curved space-time, around any mass. Okay, so we have this picture of curved space. We're suppressing the time coordinate here. To test whether space is curved, you can draw a bunch of triangles on it and see whether the interior angles always add up to 180 degrees. Every legal triangle on a flat sheet of paper has the property that the sum of the interior angles is 180 degrees. But if you put a triangle on a positively curved surface like that of the sphere, then in fact the sum of the interior angles is greater than 180 degrees. In this example, I have two lines of longitude coming down to the equator. Each of them defines an angle of 90 degrees. 90 plus 90 is already 180, and then you add the angle alpha at the top, so the total exceeds 180 degrees. Conversely, in a negatively curved surface like that of a of a saddle of a horse or a Pringle potato chip or something like that, the sum of the interior angles is always less than 180 degrees. So in fact, you could test for curvature by drawing lots and lots of triangles and seeing whether their angles always add up to 180 degrees or less than 180 degrees or more than 180 degrees. So a sphere, like this basketball, is curved. It's a positively curved surface. A flat sheet of paper is not curved. Now, it turns out that if I roll this sheet of paper into a cylinder without making any creases and without ripping it, I've not actually changed the geometry. It's still flat. Any triangle I draw on that cylinder will still have the property that the sum of the interior angles is 180 degrees. So the cylinder, though it looks curved, is in fact a flat space. Interesting, huh? We'll use that later on. Okay, well, suppose you try to put an intrinsically curved 2D surface on a flat sheet of paper. There will always be some distortions. One must keep in mind the strengths and limitations of any two-dimensional map of an intrinsically curved surface. An example is the Mercator projection of the Earth. It's very useful, we know what it looks like, but it's highly distorted. There are 4 corners, there are 4 sides, the polar regions have highly exaggerated areas. You know, how can anyone call this a reasonable map of the Earth? Well, it has its utility. Any local place preserves the north-south and east-west directions. So it's very good for navigation. You can just cruise along the ocean by having the Mercator projection. But don't try comparing the area of Greenland with that of, the United States, for example. It just doesn't work that way. I'll try to point out in the maps that I show you which aspects to believe and which aspects are distortions. Okay, so here's the geometry of a non-rotating so-called Schwarzschild black hole, as seen from the outside. This is known as an embedding diagram. It shows only 2 of the 3 spatial dimensions, and it completely suppresses time. The circles shown here are actually spherically shaped in 3D. So the event horizon of a Schwarzschild black hole is a black sphere, kind of like the black basketball. We can extend the picture inward with appropriate mathematical tricks as follows. You can see that inside the event horizon, the curves come down to a singularity, a point-like singularity in the case of a non-rotating idealized Schwarzschild black hole. I say idealized because we actually expect black holes in space to be spinning. Everything comes in with some spin, so a non-rotating black hole is probably an idealization that does not actually occur in nature. Well, in fact, the full analysis of the mathematics suggests that there's a shortcut to a very different location in our universe, or perhaps even a gateway to a parallel universe. This passage is called an Einstein-Rosen bridge, or more informally, a wormhole, as coined by John Wheeler. So in this diagram, you can see the full Schwarzschild solution. In our universe at the top, the black hole comes down to an event horizon and a singularity inside it. But look, it emerges out to another universe, forming a black hole there with an event horizon and a singularity. It's a symmetric diagram. It reminds me of my daughter Capri when she blows bubbles through a little ring like this, soap bubbles. The soap bubble is the other universe emerging at the other end of the black hole. You can also think of this as 2 black holes joined by a wormhole in our same universe, but connecting apparently distant locations via a shortcut. See, if you were to zap through that little wormhole, that would be the short way home, not the long way home going all the way around the sides there. Well, are these other parallel universes really real? They arise because they're the negative square root solution to Einstein's equations. We don't really know whether they're real. Let me give you an example. In certain physical situations, you might end up measuring the square of the mass of an object, like 25 square grams. You then say, what's the mass? 5 grams. Well, an equally good mathematical solution is negative 5 grams, because negative 5 squared is also 25. Now, we usually toss out the other solution, the negative one, as being unphysical. On the other hand, maybe it does mean something. When Paul Adrien Maurice Dirac wrote down the special relativistic form of the main equation of quantum mechanics, the Schrödinger equation, he realized that it suggests the existence of an anti-electron, a positron, a particle having all the properties of electrons but with a positive charge. He predicted its existence. And in fact, some years later, positrons were actually found in nature. Now, some physicists say that any valid solution of a mathematical equation always corresponds to reality in nature. We don't really know whether that's true. You can predict, for example, in special relativity, that there are particles called tachyons. They always travel at a speed faster than that of light, rather than slower than that of light, like other particles, tardions were called. We've never detected tachyons. On the other hand, they're hard to detect, so maybe they exist. So, in a similar way, we don't really know whether this other parallel universe exists, but mathematically it is a valid solution to Einstein's equations. Well, one limitation of the previous maps is that they don't show time and they don't show the interior of the black hole very well. So we're going to use what's called a space-time diagram. These are usually arranged in such a way that light travels along a 45-degree line. So x, space, is to the right, time is vertically upwards, and light travels along a 45-degree line. You can make this work out if you make 1 light year along the spatial direction be an inch, and 1 year in the time direction also be an inch. Light travels 1 light year per year, and so it'll go along a 45-degree line. If you're at the origin of coordinates there, your future is the cone that's above you. You can go anywhere into that cone, not quite along the 45-degree lines that light follows, because you can't travel at the speed of light, but anywhere upwards. And you came from somewhere in the past. The regions marked elsewhere cannot be reached because they would require you to exceed the speed of light. You would go, for example, 2 light years in 1 year. There's a joke. How does Einstein begin a story? Once upon a space-time. Well, you see here, we're referring to the space-time diagram. So you can't just say once upon a time. You can't just say something is happening here. You have to state where it's happening and when it's happening. Once upon a space-time. Now, the general relativists Martin Kruskal and Peter Tsakiris developed some nice space-time diagrams appropriate for black holes. And Roger Penrose made some significant modifications. So these diagrams are now generally known as Penrose diagrams. The space axis is horizontal, time is vertical, and light travels along a 45-degree line. So the Penrose diagram counterpart of the Schwarzschild geometry that I showed earlier looks like this. Our universe is that square on the right. It's obviously highly distorted because the whole universe is filled into a square, even if it's an intrinsically infinite universe. The black hole is off to the upper left. The singularity is the structure marked with teeth at r equals 0, kind of like shark's teeth. You don't want to go there. Light travels along 45-degree lines. A valid trip for you might be trip A, along that green arrow. You're going forward in time and a little bit to the right in space. That would be a fine trip to make, down to your local grocery store or whatever. But a silly trip to make would be the one marked with a blue line, where you go beyond the horizon and then you inevitably hit the singularity, because once you've crossed the horizon, you can't get out, because you can't go more steeply than a 45-degree line from the vertical. And so you can't get back out through the horizon, since the horizon itself is a 45-degree line from the vertical. That's the basic problem. So you're doomed. Well, this is a pretty informative diagram. It shows you pretty directly why you can't get out once you have crossed the event horizon. But once you cross the horizon, you see a very interesting thing. Putting yourself at the point there, you can see that light rays from the horizon you crossed will reach you, but light rays from what I call the anti-horizon will also reach you. So you see 2 horizons. This is why, fundamentally, in the previous lecture, the single horizon split into 2 once we crossed the horizon. You see both coordinate grids. But now suppose we want to include the other parallel universe in the full Schwarzschild solution. Here's the corresponding Penrose diagram that applies to this particular physical picture. In addition to our universe, you now see the parallel universe to the left. Okay, it has event horizons, just as ours does. A person in that parallel universe could cross his or her horizon and end up in the black hole. You also see that, in fact, you can't cross from our universe to the parallel universe, because to do so would require a path that's inclined by more than 45 degrees to the vertical. That is, a path that is only traversable if you were going faster than the speed of light. So mathematically you might traverse the wormhole, but physically you can't do it because you'd be going faster than the speed of light. So it's impossible to go through a wormhole connected to a non-rotating black hole. Don't try it. There should be a warning sign. Stop! Don't go any further. Don't cross the horizon. It'll be dangerous to do so. Now, another interesting thing about this diagram is that there's this object called the white hole, sort of at the bottom. That's like the time reversal of a black hole. Instead of objects falling into it and never being able to get out, objects come out of a white hole and are never able to get back in, because they can only go forward in time, basically in the upward direction. And these anti-horizons and parallel anti-horizons are 45-degree lines, the lines along which light travels. So once something gets out of a white hole, it can't get back in. For a short time, before quasars were understood to be supermassive black holes accreting gas, some people speculated that they might be white holes from which energy is emerging. Well, in fact, their properties don't look like those expected of white holes, and we don't know of any real objects that resemble white holes, so we've never found them. They probably don't exist. How about rotating black holes? Might we be able to traverse a rotating black hole? What does the mathematical structure of a rotating black hole look like? Well, the mathematics of a rotating black hole was figured out in 1963 by Roy Kerr, many decades after Schwarzschild figured out the non-rotating black hole. It's very much more complicated mathematics. There are two horizons, an inner horizon and outer horizon, and also a ring singularity. I briefly mentioned this in Lecture 1. Now, if you look at the Penrose diagram of the rotating black hole, it looks very complex. Again, remember, time is vertical, space is horizontal, and light travels along 45-degree lines. Now, in addition to our universe and the parallel universe of the non-rotating black hole, you see a whole bunch of new universes and new parallel universes higher up in the diagram. The singularity, rather than being horizontal, as in the non-rotating black hole, is now vertical. That's an interesting aspect of the non-rotating black hole. The singularity was horizontal. It then is space-like. In other words, it occupies much of space, and you will hit it at some particular time in your future. That's why you can't avoid the singularity in the non-rotating black hole. But here in the rotating black hole, the singularity has become time-like. It has become vertical, as you can clearly see. So in fact, you can, in principle, choose paths that avoid it. You can go along the wavy line, going into the inner horizon, through the wormhole, back out of the other inner horizon, emerging through a white hole into some other universe. Crazy, it seems, huh? Fantastic. Well, you can also conceivably travel into what we call the antiverse. That is, go through the time-like, the vertical singularity, and end up in that region called the antiverse. That would be equivalent to travel through the ring singularity. Basically, you get whipped around by centrifugal forces, forces that are felt in a rotating frame of reference when you go through the ring singularity, and you end up in this weird antiverse. Crazy, huh? Here's sort of the diagram that allows you to see space-time flowing in to a rotating black hole in one direction. Those are the light blue arrows, and then coming out after having gone through the ring singularity into the opposite direction. Well, it turns out that though this idealized mathematics suggests that the wormhole of a rotating black hole is traversable, and even that the singularity is traversable, it turns out that a whole bunch of mass and energy builds up at the inner horizon. All this stuff that's streaming in collects up there and actually hits material that's streaming out. You can actually see in this diagram here material streaming through the inner horizon, but also streaming out of the inner horizon a bit further along. So different particles of matter can, in fact, hit each other and collide, and they create a tremendous amount of energy, a tremendous amount of heat, and you would get roasted, you would get fried, you would get vaporized at the inner horizon. In fact, this so-called mass inflation instability doesn't even let the wormhole form. It closes the wormhole. It shuts it down. And indeed, it makes the singularity point-like again, like in a non-rotating black hole, not ring-like. So there's no way you can traverse a real wormhole connected to black holes, that is, having horizons. Kind of a bummer, okay? All these, science fiction movies, they're probably wrong, in case you didn't guess that already. Here's a diagram that shows you the inner horizon and the ingoing and outgoing particles and radiation. Inside the inner horizon, a tremendous amount of material builds up, sort of a hot plasma. It would just completely roast you. And there's the point-like singularity in the middle. So the whole character of the rotating black hole changes when you realistically take into account the fact that stuff has been falling into it. Okay, well, what about charged black holes? Might they be different? Well, we don't expect significantly charged black holes to exist in nature. They would quickly attract opposite charges from outside the event horizon and neutralize themselves. But let's consider them anyway, just for fun. By the way, these charged and rotating black holes, the idealized kind that never have anything fall into them, are open and are traversable, but the catch is that, if you try to traverse them, then you create these mass inflation instabilities and everything falls apart. So here we're talking about real black holes. Maybe in the science fiction movies and books, they're talking about idealized black holes, but in that case, nothing could travel through them anyway, it turns out, okay? All right, well, it turns out that the mathematics of charged black holes was figured out around 1920 by Hans Reissner and Gunnar Nordstrom. I doubt that Gunnar Nordstrom was related to the Nordstrom of high-end department store fame. Okay, so here's the Penrose diagram of a charged Reissner-Nordstrom black hole. It looks similar to that of a rotating black hole. In particular, there are outer and inner horizons, there's a wormhole, and so on. The angular coordinates differ, but they aren't shown here. Again, it looks like you can travel to other universes, the antiverse, the new universe, the new parallel universe, and so on. And even perhaps go through this singularity. Kind of like in the case of the rotating black hole, but in this case, you can go through the singularity not because the centrifugal force whips you around, but because the electric field has what's called a negative pressure associated with it that keeps the singularity open and, well, keeps you from actually hitting the singularity and kind of repels you away from it through to this other universe. This is really all pretty heavy-duty relativity, folks. The flow of space-time diagram associated with a charged black hole is shown here. The light blue arrows show space falling in faster and faster, but then the dark blue arrows show it coming out again, at least in the idealized situation. But again, as with the rotating black hole, in fact, the wormhole gets destroyed by all the material collecting up near the inner event horizon. You would be vaporized at that point. Well, suppose wormholes really do exist. Suppose you forget about the practical difficulties. Wouldn't it be fun to actually simulate what you would see if you were to go through one? Well, Andrew Hamilton does this on his website at the University of Colorado. He shows what you would see going through a charged black hole. And you would see something similar if you were to go through a rotating black hole. The backdrop is once again Axel Mellinger's wonderful Milky Way panorama. Once again, we have a map showing a free-fall trajectory. The green region represents stable circular orbits. The yellow region represents unstable circular orbits. They could be stabilized if you were to fire your rockets, but in the absence of rockets, they are unstable. The orange region has no circular orbits unless you fire a rocket. The red circles are the horizons, and the red area is the space between the horizons. The blue circle is the radius of closest approach to the center. Time, again, is measured on this clock. This is the time in seconds. for the supermassive black hole in the Milky Way galaxy. So if you were to go from the outer horizon of that black hole to the inner horizon, where you would be vaporized by all this radiation and matter, it would take you 20 seconds. Let's fall in and see what it looks like. Oh man, look at those gravitational distortions. Look at the Einstein ring. The black hole is growing as you get closer and closer to it. You see the coordinate grid with both the north and south poles of the black hole. There you went through the event horizon. It bifurcated into two because you see your horizon and the anti-horizon. Now you're going in. Ooh, wow, there, you hit the inner horizon and you were destroyed by the mass inflation instability. But let's say you weren't destroyed. Now you're going through the wormhole. You're traversing it. And you're about to hit the other inner event horizon. There you go. Bam! There's a lot of light concentrated there. Now you're going out into the other universe. The black hole's size first grows, then recedes a little bit, and now you've emerged into the other universe where you might emerge near some edge-on galaxy like this. Now let's say you turn your gaze back toward the black hole. You see material emerging from it. You see essentially your universe back there trapped within that circle. Oh, that's just so much fun. It's just so much fun. If we dissect this in some more detail, you can see that as you go through the outer horizon, you can see this distorted coordinate system with both poles. The plane version looks a little bit more boring. You can't tell you've gone through the outer horizon in the plane version. Nothing looks different from a moment before or a moment after. When you cross the horizon, the coordinate grid splits into two. Without the coordinate grid, you don't see anything particularly different. Again, you can't tell that you've crossed the outer horizon. Looks about the same. But then the black hole starts to shrink, interestingly enough, once you've crossed that outer horizon. The coordinate grids look very complicated. Without them, the picture looks something like this. Now you go through the inner horizon and flash. There's the giant flash of light and particles at the inner horizon where all this stuff collects and vaporizes you. Oh, now let's go through the wormhole itself. We're traversing the wormhole like in a science fiction movie. And we come back out, but before coming back out, we have to pass through the inner horizon again. So there's another flash of light. Blam! Right there. Okay, you're out of the wormhole. Now you're going into the other universe. Okay, so you emerge into the other universe through what looks in that universe to be a white hole. You can come out of it, but you can't go back in. So now you're in the new universe, and you see a flash of light corresponding to all the material that was sort of concentrated in that black hole from the other universe. Now you gaze at a galaxy in your new universe. And if you look back at the white hole, you will see all the material in your other universe within those circles there. Wow, what a trip. What a trip. But perhaps it's a good thing that wormholes, traversable wormholes, don't really exist. If they did exist, they might allow travel backward in time to our universe. Oh man, that would be bad. Because, look, if you consider this Penrose diagram, which I've drawn in flat space, but then you recall that taking flat space and forming a cylinder out of it doesn't fundamentally change the geometry. It only changes the global topology. Well, that would suggest then that you could go upwards in the Penrose diagram, bend around, and then come back to the place from which you started, or even to a place before the point in space and time at which you started, right? This is no different geometrically from the Penrose diagram that I already showed, but it is different topologically. Well, that's really neat. So there could be a way of traveling back in time in our universe and altering history. For example, you could prevent your parents from ever meeting. So how would you ever have been born? Physicists don't like this. Physicists don't like what is called violations of causality, violations of cause and effect. So it's a good thing that this probably really doesn't happen in real life. But sometimes you see these hilarious ads. Here's one: wanted, somebody to go back in time with me. This is not a joke. Then they give an address. You'll be paid after we get back. Must bring your own weapons. Safety not guaranteed. Hey, by the way, I've only done this once before. Well, when Carl Sagan was writing Contact, he actually had to use idealized black holes and wormholes because traversal through a real one wouldn't have been possible. You know, maybe there's ways of doing it, but we really don't know how to do it. So anyway, let me conclude by saying that although travel through wormholes is a popular theme in science fiction, it really almost certainly is not possible. Any realistic situation, including all the matter and radiation, seems to scrunch up the wormhole, fry you, vaporize you, and so on. Turn the singularity, for example, from a ring singularity into a point-like singularity. If it were possible, we would have to worry about violations of causality. You know, many books, movies, and television shows have had much fun with such concepts, especially travel through wormholes backward in time. That's a favorite topic. They've also invoked faster-than-light travel speeds, which similarly allow people to travel back into the past, at least in principle, if you study the special theory of relativity. If these possibilities were true, then perhaps I wouldn't even be here to give these lectures, because something in my future might subsequently prevent me from ever having existed. Now, I hope you agree that this would not be an acceptable outcome. Thank you.